Welcome once again, chemistry classes. From Spark Academy. So we are in chemical bonding. We started already. We are learning chemical bonding. In that, covalent ionic compounds completed. Poisson rule also we completed. Bond parameters started. In that, few bond parameters also we completed. Now we see today again bond parameters. In that remain bond parameters. So weightage for chemical bonding, 1 mark, the one question. So sometimes we have a chance to get from these bond parameters. So before that, use my coupon. Yes, ACI and 10. It is my coupon. Students, use this coupon. So bond parameters. So what are bond parameters? Terms which are connected with bond. So terms which are very useful related to the bond. Such terms are called here bond parameters. Clear? So these are called here bond parameters. So what is the first bond parameter? So bond parameter, first one here, bond length. Second one, bond angle. Third one, bond energy, enthalpy. Bond order. So we completed bond length, bond angle, bond energy or enthalpy, bond order. In this session, now we are going to clear the resonance dipole moment. This dipole moment also called bond polarity. Now first, resonance. So what is resonance? Resonance is a Lewis structure. So according to Lewis given resonance structures of the Lewis structures of the molecules. So those molecules, they are showing how many bonds present within a molecule, how many excess electrons. So that structure is called Lewis structure. So Lewis structures in that pi electrons, they delocalizes. If pi bond there, pi electrons delocalizes. Due to the delocalization of the pi electrons, we get the different structures. Such structures are called resonance structures. So now clear about the resonance structures. So this process means when they are showing resonance structures, that phenomena is known as resonance. Now see here, so we have here molecule O3. What is the name of the O3? Ozone. Ozone has how many atoms? So ozone has here 3 atoms. So what are they? Oxygen atoms. So what is the atomicity of the ozone? Ozone atomicity is 3 because it contains 3 atoms. Now come to the structure of the ozone. So this is the hybrid structure of the ozone. But we have here ozone's 2 canonical structures. What is the first one? This is the first ozone's canonical structure. This is the second one. So how we got from that structure to this structure? Otherwise, from this structure to that structure. It is only possible by only what? Delocalization or transfer of the pi electrons. Here this side between two oxygens, two bonds present. So first bond is sigma bond. Sigma bond contains sigma electrons. Second bond is pi bond. So pi bond contain here pi electrons. These pi electrons delocalizes means transferring. See how they transfer this side. Okay, due to the transfer of here we got here one more structure. So this structure is called resonance structure of the one more structure of the ozone. It is called resonance structure. Now see here, what is the difference? Only pi electrons they transferred this side. What about these pi electrons transferred this side? Result. So what is the result here? So result here, okay, bond. Okay, which bond? Result here, pi bond. But due to that reason, what we are getting here? So we got here what? We got here, okay, structures. So structures are called canonical structures or resonance structures. Canonical structures or resonance structures. Now after learning resonance structures or canonical structures of the ozone, we have to find out the bond order. So what is the bond order of ozone? So bond order is equal to S. Okay, number of bonds surrounded by the central atom. Here see, in the case of the ozone, this oxygen is what? Central atom. So number of bonds surrounded by the central atom, how many bonds there? 3 bonds there. Yes, 3 bonds present. 3 bonds. 3 by resonance structures, how many there? 2. Then 2 ones are 2 twos are. So yes, 2 ones are 2. So what is remain here? 1. Then okay, what is the here bond order? 1.5. Yes. See, by this way, resonance structures here very useful to get the bond order of the molecule. So here, what is the bond order of the ozone? Here we got the bond order of the ozone. So what is the bond order of the ozone? Yes, bond order of the ozone is 1.5. 1.5. Yes, clear? So can I repeat once again? What is the bond order? Number of bonds, okay, by central atom, surrounded by the central atom, and how many resonance structures. So we will get the bond order of the corresponding molecule. Now next molecule, see what is this molecule? Boron Trifluoride. So what is the central atom in boron trifluoride? Boron. Boron has how many fluorines? 3. Now we see the structure. See, boron is the central atom. Boron around how many fluorines there? Fluorine number 1, 2, 3. 3 fluorines there. Now see here. So every fluorine after combining with the boron has excess electrons how many? 1, 2, 3, 4, 5, 6. Here also 1, 2, 3, 4, 5, 6. By this way, each fluorine which is surrounded around the boron has 6 electrons. So now see the boron valency here. So boron valency here how much? So boron valency here, okay, fulfilled. No. Boron valency here not fulfilled here. Yes, because boron valency here still, okay, less than 8. So boron does not contain here octet electronic configuration. Now see the boron. So how here stability increases in the case of the boron trifluoride. So any one fluorine has a chance to form the back bond. So here this fluorine formed back bond. If one fluorine is formed back bond, no chance to form another fluorine's back bond. Now what about in the case of second structure? Second fluorine is formed. What about in the case of the third structure? Third fluorine is formed back bond. As clear? So by this way, boron trifluoride has how many canonical structures? So boron trifluoride, due to the formation of the back bond of the fluorine in every structure, so we got here 3 resonance structures of the boron trifluoride. So how many structures? 3. So it is a number 1 structure, it is a number 2, it is a number 3. So 3 resonance structures possible from the boron trifluoride. Now can we check its bond order? Yeah, what is the formula of bond order? Yes, bond order in the case of the molecules which are showing the resonance structures, their bond order we can get by this trick. Number of bonds surrounded by the central atom. How many bonds there around central atom? So what is the central atom here? Boron. So boron central atom, bond order. Now how many? Yes. How many bonds? 4. 1, 2, 3, 4. Now next. How many resonance structures? 3. Yes. 3 bonds are 3. Yes. What about remain? Remain is what? 1. Yes. Then again, it will go 3 3s are 9. Yes. So how much here? 1.3. Again 3. Then what is the bond order of the boron trifluoride is 1.33. Yes. It is a 1.33 bond order of the boron trifluoride. Clear? Yes. Now next we check. Yes. Next we are going to check now as bond order. Yes, students, clear this one, bond order. How to find out the bond order? Especially in the case of the molecules which are showing resonance structures. So our first bond parameter is resonance structure. Now next one, what is this? CO3. CO3 2 minus. It is ion. What is the name of this ion? Anion. Carbonate anion. Yes. Carbonate anion. Showing resonance structures. So carbonate anion showing how many resonance structures? So first I write here CO3 2 minus. It is a what formula? Here is the first structure. So central atom is what? Oxygen or carbon? Carbon. So how many here? Other than central atom, how many present here? Yes, they are present here 3. Clear? 3 they are present. Check. Now here see how many excess electrons of the oxygen here, means lone pair 3 here 2. So here charge is there. So this is shifting this side. Now due to that shifting here we got the double bond, and this charge is shifting this side. After see shifted here, then here double bond. Yes, clear? Now what about this bond shifted up? This bond shifted this side. Due to shifting we got here structure. So that is actually not shifting. It is called what? Transfer of the pi electrons. So what about now? We got here negative charge. So here negative charge already present. So here 2 lone pairs there. Now this negative charge is shifting this side, means pi electrons or excess electrons. So like the first one, first which oxygen? Here electrons they are transferred this. Next this oxygen. Now has a chance to transfer of this oxygen electrons also. By this way, carbonate anion shown here how many resonance structures? We got here carbonate anions 3 resonance structures. So carbonate anion has 3 resonance structures. After getting the resonance structures, what is our function? Find out its bond order. So what is the bond order of the formula? Number of bonds same. Just now we learned. Now we see number of bonds surrounded by the central atom. How many bonds there? Yeah, bonds here, 4 there. Yes. How many atoms? Sorry, how many resonance structures? Resonance structures 3. Yes. So then what is the bond order? 1.33. Yes. Okay, like the previous molecule, this molecule has same bond order, that is 1.33. So it is the bond order of the carbonate anion. Carbonate anion. So after carbonate anion, the next very important molecule is benzene. Benzene. What is the formula of the benzene? C6H6. So benzene we seen so many times in our class. So now once again the benzene, but here we are seeing its what? Resonance structures. Now see, benzene has how many resonance structures? Benzene has 2 resonance structures due to the pi bonds. How many pi bonds there in benzene? 1, 2, 3. Pi bond contain pi electrons. They are delocalized electrons. They are what? Transferring one place to other place in within a benzene molecule. Due to that reason we got one more resonance structures. By this way benzene has 1, 2 resonance structures. Here students will think it is the third resonance structure of the benzene. No, it is the benzene's hybrid structure. So benzene has only 2 resonance structures. Now what is the bond order of the benzene? Benzene bond order is 1.5. Why? Because we have to take only how many bonds? It's 1.5 means. 3, yes. Then only we take how many here? Yes, atoms 2 only. So we got here 1.5, the bond order of the benzene. Clear? Yes. So here we completed the first bond parameter. So what is the first bond parameter we learned? So resonance. After resonance, the second bond parameter and last one in our bond parameters, that is dipole moment. So what is dipole moment? When it rises. So what is the use of the dipole moment? If dipole moment is there or not in given molecule, is it depends on the symmetry of the molecule or not? So all things we see in this dipole moment. Dipole moment rises in any system in which there is a separation of the charge. You take any system, means any covalent molecule, but this separation only possible due to the electronegativity different. Where? In covalent bonds. In covalent bonds, charge is possible? Yes. Covalent bonds, we know they are 2 types. Same elements contain covalent bonds. Different elements contain covalent bonds also present. So different elements, if in that electronegativity is different is there. Due to electronegativity different, there charge will form. The charge is separating which are held together in a molecule. They may be atoms or what? Ions. So this electronegativity different makes that atom into the dipole moment. Clear? Now we understand when dipole moment is possible. Yes, what is the first condition for dipole moment? Covalent compound contain different elements. It's mean, what about different elements means? They have what? Electronegativity different. That electronegativity different only forms what here? Charge. So that charge separates which are present inside the molecule. Now a bond, dipole moment is measured, yes, polarity. So if here one, for example A and B, 2 atoms there, are they same or different? A and B, they are same elements or different elements? Different elements. Then here electronegativity different is there. Then we can say this molecule is polar. So here dipole moment useful to know the polarity of the molecule. It involves the concept of electric dipole moment, which is measure of the separation of the negative, positive charges in the system. The bond dipole moment is called vector quantity. It has both magnitude and direction. So here these are the parameters about the dipole moment. Clear? Now we see the example here. So what is the name of this molecule? HCl, hydrochloric acid molecule. This hydrochloric acid molecule, what type of bond there between them? Don't say it is the ionic, because showing their charges. Due to the charges, students they can expect this is a what? Ionic compound, but it is not a ionic. It is a what? Covalent molecule. But why here rose charges? So here we got charges. Why we got charges? Due to the electronegative difference. So hydrogen chlorine, are they have same electronegativity? No. Here electronegative element is chlorine and hydrogen is very less. So due to electronegativity, chlorine has a chance to attract the bonded electron. So that result is what? Partially negative charge upon the chlorine. Yes. What about hydrogen? Is it attract the bonded electrons? No. Because compared with chlorine, it has the less electronegative character. Due to that reason, it loses bonded electron. Then here hydrogen got what? Partially positive charge. So this partial positive negative charges separated atoms or constituents which are present inside the molecule. So this poles, they shows what? Dipole moment. So dipole moment has a magnitude and a direction. So here direction showing what? So dipole moment what? Due to chlorine. So that's why dipole moment has a magnitude and direction. Now see here, same thing which I explained here, they given. We are showing here down also. As the two, this molecule contain what here? S2 charges. Yes, charges there. What is first one here? Positive, negative. Two electric charges that rise in a molecule. Yes. So both are opposite. So this total separation is called distance. This distance is denoted by D. Yes. So clear about the HCl molecule? Yes. If here HCl molecule we understood clearly. Yes. Then we go as next one. What is the next one now? Yes. Next one is dipole moment and its formula. A dipole moment is the product of the magnitude of the charge and the distance between from the centers to the positive negative charges in a molecule like HCl. Just now we seen the HCl, yes. So HCl, yes, positive negative charges. So it is denoted by Greek letter. What about the mu? Dipole moment. So dipole moment m mu is equal to charge, that is a q. Distance of the separation, that is radius. Clear? So now what are the units of the dipole moment? So dipole moment we can measure by Debye's units. So the Debye's denotes by D. So 1 Debye is equal to how much? 1 Debye is equal to 3.33564 into 10 to the power of minus 30. What about it is? Coulombic meters. Cm means not centimeters. Coulombic meters, yes. In Coulombic meters, we can measure the dipole moment. So these are the units for dipole moment. So here dipole formula, dipole moment, both are required for us to do the sums. Next, the dipole formula. we learned here, yes, what is the dipole moment? Mu. It also vector quantity as direction is parallel to the bond axis. In chemistry, arrows that are drawn in order to represent dipole moment begin at the positive charge and end with this what arrow at negative charge. Means we started from the positive charge in a molecule and end at the negative charge. When two atoms are different, then only we say electronegativity interaction takes place. That electrons tend to move from their initial positions to come closer to the more electronegative atom as due to what? Electronegativity. This movement of electrons can be represented via the bond dipole moment. So we represented already here, okay, dipole moment in the case of the X here. So same thing again we are learning here, yes. Clear? After learning successfully the dipole moment and its formula, units, so now we see examples. So first example, dipole moment of beryllium fluoride. So beryllium fluoride dipole moment, yes. So beryllium fluoride, what is the central atom? Beryllium. So beryllium, each side fluorine, two fluorines totally, yes, and they formed single bonds, no any double bond. Now beryllium and fluorine, so which is the more electronegative atom here? So in the case of beryllium fluoride, fluorine is electronegative element. So here fluorine, here two fluorines, they are electronegative. Then what about here? What about here? Here direction shifts which side? Fluorine side. This side also shifted towards fluorine. Yes. Now what is the dipole moment in the case of the beryllium? So first here from central atom to what? Electronegativity. Yes. Direction shifting towards the two fluorines, same opposite direction. Then here dipole moment becomes 0. It is a one explanation. So one more explanation is beryllium trifluoride, even it has electronegativity difference between the beryllium and fluorine, but due to the symmetry, yes. So beryllium difluoride is the symmetrical molecule, so it has the same symmetry. Due to that reason also its dipole moment is 0. So from this molecule we concluded what? So from central atom to, so dipole moment direction, the ends of the molecule or atoms like fluorine, then dipole moment is 0. Second thing, this beryllium trifluoride, due to symmetry, its dipole moment becomes 0. S. So two ways we explained the dipole moment of the beryllium trifluoride. S. Now dipole moment of the water. Yes, water. Water is oxygen hydrogen, otherwise hydrogen oxide. So what is the central atom in the case of the water molecule? Central atom is oxygen. So oxygen surrounded by two hydrogens. S. Clear? Now two hydrogens and oxygen. So which is more electronegative element here? So more electronegative element here in the case of the water molecule, oxygen. So oxygen is due to electronegativity. The dipole means the arrows shifts towards the oxygen. S. So this shape of the molecule explained by VSEPR theory, yes. Valency shell electron pair repulsion theory explained about the water molecule, yes. Now come to the dipole moment. So dipole moment in the case of the water molecule, how much? 1.84 dBs. Okay, why? Because the bond angle in water molecule is 104.5 degrees. Yes, if we see the individual bond moment and oxygen hydrogen. So here oxygen hydrogen bond is there. So due to this oxygen hydrogen bond, it has the dipole moment. That dipole moment is 1.5 device. So that side 1.5 device, this side that 1.5 device. So now we have to make it net dipole moment. The complete molecule dipole moment, net dipole moment is 1.84 device. So now according to the second method, what symmetry or unsymmetrical? So what about the water molecule is symmetrical or unsymmetrical? So water molecule is unsymmetrical. Why? It is not in the linear like beryllium fluoride. So beryllium difluoride, it is a linear molecule, but here water molecule is not linear. It is in bent or angular shape. Now here dipole moment not equal to 0. With a second explanation also we say. Yes. So now clear here. So water has dipole moment. That net dipole moment is there, and according to the structure it is unsymmetrical. So its mu not equal to 0. It has what? How much dipole moment? It has 1.84 device. That is the dipole moment of the water molecule. Clear? Yes. Next. Now dipole moment. Yes. So how? Just now I said dipole moment. Yes. With the help of what? Symmetric. Molecule symmetrical or unsymmetrical. Now we take the symmetrical molecule. Yes. All have electronegative different here. Beryllium chloride, boron trifluoride, methane, carbon tetrachloride, carbon dioxide, phosphorus pentachloride, sulfur hexafluoride, iodine heptafluoride. But all have electronegativity different, but they are symmetrical molecule. So symmetrical molecule means their mu is equal to 0. Mu nothing but dipole moment. So dipole moment here 0. Now unsymmetrical molecule, yes, SO2. Central atom sulfur contain what here? Lone pairs. NH3 central atom nitrogen contain lone pair. H2O central atom oxygen contain lone pair. BRF3 central atom boron contain lone pair. Chlorine also contain lone pair. Due to lone pairs, their structures are unsymmetrical. So unsymmetrical molecules dipole moment not equal to 0. Yes, it is not equal to 0. Clear? So by this way, symmetrical molecule dipole moment is 0. Unsymmetrical molecule dipole moment not equal to 0. Clear? So here we concluded dipole moment clearly. The molecules, even they have the electronegativity different. Clear? Yes. Now we do calculation. Yes. Calculate the percentage ionic character of HCl molecule. Yes. HCl is what type of molecule? HCl is a covalent molecule. HCl as covalently bonded as hydrogen chlorine, but does it contain ionic character? Yes. How? Due to the electronegativity different. Yes. Hydrogen chlorine, they have electronegativity different. Due to that electronegativity different, chlorine has what here? Partially negative charge, and hydrogen partially positive charge. Positive negative, that makes the separation of the atoms which are present in a molecule. Now here, yes, due to this reason, here this HCl covalent molecule, even it has ionic character, but how much it has ionic character we don't know. Now we are going to calculate ionic character of the HCl molecule. The bond length they given, yes, bond length they given 1.275 angstrom units. And observe dipole moment, yes, when dipole moment also there in the case of the HCl, we learned it just now. How much they given here? Dipole moment 1.03 dBars. Yes. So question, if we understand, we proceed into the answer. Yes. Solution. So given dipole moment of HCl how much? 1.03 dBars. It is a given. Next, theoretically bond length 4.8 into bond length. Yes. This is the according to the theory. Yes. Now percentage of the ionic character. So dipole moment, experimental dipole moment, and which we got from the theory. Yes. Now how much experimentally they given? 1.03. Yes. What about here? Bond length of HCl molecule 1.275. So what about they given here? 4.8, that is theory value. Now, so into 100 we are going to find out what is ionic character. These three things here gives the what here? Percentage of the ionic character of the HCl. Even HCl is a covalent molecule, but it has the ionic character. How much? So 17% ionic character present in HCl molecule. Yes. So by this way, we have to find out ionic character of the covalent molecules which have dipole moment. Yes. So as Spark Store long-term courses. So admissions open, join now. So we providing the classroom coaching, offline, online. As here about details of offline. So short-term, regular, both are available. Yes, our branches, Narayanpura and Mehdipatnam. See, call on these numbers and book your seats. As this is our daily lessons, daily sessions, test details, and our methodology. What is the first one? Basic concepts, shortcut methods, all model questions, exercise questions, chapter-wise tests, weekend, grand, test analysis along with. So our about our Spark Academy. Why Spark Academy? Here personalized coaching, good faculty, highly experienced, orientation coaching, and we have only limited batch size. So these are our side hybrid coaching, online coaching. See from our side the study material and books, access to online, classroom and doubt clarification things present. Join now on our Telegram link also to get the some topics with examples. After this we see some examples for dipole moment. Yes, the first question. Which of the following set of molecules will have zero dipole moment? Yes. So dipole moment that is depends on molecule symmetry or unsymmetry. Yes. So which of the following set of molecules will have dipole moment? Yes. Now they give an option. First one, ammonia. Yes, ammonia is has dipole moment. Yes. So its dipole moment mu is equal to 0. No, not equal to 0. Why? Because in the case of the ammonia, nitrogen is the central atom. So nitrogen has excess electrons. Then ammonia geometry is pyramidal. So due to pyramidal shape, its geometry is not symmetric. it is unsymmetrical molecule, then its dipole moment is not equal to 0. So we got first set, first molecule only, the dipole moment not equal to 0. Now second, so boron trifluoride, hydrogen fluoride, carbon dioxide and 1,3 dichlorobenzene. Yes. So 1,3 dichlorobenzene here. So boron trifluoride, hydrogen difluoride, carbon dioxide 1,3 dichlorobenzene. Yes. Here hydrogen fluoride is not a S. Okay, we say it is mu not equal to 0. Then, so this option also wrong. Second also. Now, nitrogen trifluoride, beryllium trifluoride, water dipole moment is not equal to 0. Yes. So, this option also wrong. Now, what about the boron trifluoride? Boron trifluoride. So, planar molecule, 0 dipole moment. Beryllium difluoride we learned. So, it is linear. Carbon dioxide also linear, mu is equal to 0. 1,4 dichlorobenzene, yes. Benzene has here two substituents. One is what? Para. One is what here? Para. So it is 1, 2, 3, 4. 1,4 dichlorobenzene, yes. These all molecules, what dipole moment is 0. So what is the set of molecules? Answer is 0. Yes. Now answer is what? D. Yes. So D, the set of molecules, they contain dipole moment, okay, is equal to 0. Clear? Now next question. Which of the following is the correct order of the dipole moment? Yes. So now dipole moment we check NH3 less than BF3. No, BF3 is dipole moment 0. NH3 is as. No, it is less than, it is possible. No. So first option, the A is the wrong here. Sixth. Now what about BF3 is less than NF3 and NF3 is less than NH3. NH3 is less than H2O. Yes, correct. So what about here? BF3 is less than NH3. Okay, NH3 is less than NF3. Wrong. Because NH3 compared with NF3 more dipole moment. What about H2O less than NF3? NF3 less than NH3. NH3 is less than BF3. So this option also wrong. That's clear? So what is the correct option here? Correct option is here. Which one? Here, which? Yes, B. Why? Because here BF3 dipole moment is 0. Now NF3 has less than the BF3. Sorry, NH3. NF3 less than the NH3. NH3 is less than the H2O. Yes, correct. So what is the answer? Answer is B is correct. Now next. Which of the following molecules has the maximum dipole moment? Yes. So which one has here maximum dipole moment? CO2. First we take. What is CO2? Carbon dioxide. So linear molecule. So dipole moment is equal to 0. Now CH4 central atom is the carbon. And what about how many hydrogens therefore? So it is tetrahedral geometry, mu is equal to 0. So same symmetrical molecule it is. Now come to the NH3 and NF3. Both are unsymmetrical. But here compare with nitrogen, fluorine has the more electronegative S. So we draw the structure. Now here goes the credit to dipole moment which side? Fluorine side. So central atom becomes here 0. But in the case of the NH3, yes. So that central atom is nitrogen and remainder hydrogen. Now here arrow mark goes towards the nitrogen. So answer is which one here? C. So here ammonia has maximum dipole moment in given molecule. So answer is which one? Ammonia. Yes. So after ammonia, this next. The electronegativity difference between N and F is the greater than the than that between N and H. At the dipole moment of NH3 is 1.5 dBs. So what about in the case of the NF3? 0.2 dBs. Yes. So why? Okay. Yes. This is because why? This situation is there. So here we have to understand the question. As so this question is like a description. Here first you read once again the question and have a you have to understand. Here in the question, okay, talking about the what? Electronegativity, difference between nitrogen and fluorine in NH3. No, nitrogen and fluorine is greater than the N and H. Yes, at the dipole moment. Yes, but even here ammonia has the larger than that of NF3. Why? Reason. So what is the reason in the case of this question? Yes. So now in NH3 the atomic dipole and bond dipole are the opposite direction, whereas NF3 these are in the same direction. So here opposite direction? No. Yes. So the first option is wrong. Now in NH3 as well as NF3 the atomic dipole and dipole are in the same direction? No. Because here in the case of NH3 that goes to nitrogen. In the case of NF3 from nitrogen to goes to fluoride. So that's why the option B is wrong. In NH3 the atomic dipole and bond dipole are the same direction, where in the NF3 these are in opposite direction. Yes. So in the case of the dipole and bond dipole are the same direction towards the nitrogen in the case of the ammonia. But that is different in the case of the NF3. Then we can say direction is same way? No, opposite direction. So here the answer C is the correct explanation for the question. Now NH3 as well as NF3 or the atomic dipole and bond dipole are in the opposite direction? No. NH3 to compare NF3 is opposite, then option D also wrong. So what is the correct option regarding this example question? Yes, here regarding this example question, the correct explanation answer is C. Yes. So due to that reason only, NH3 dipole moment is larger than NF3. Next, which of the following would have a permanent dipole moment? Yes, question number 17 talking about the permanent dipole moment. Yes. So which one has here permanent dipole moment? Question number which one? Yes, 5. Example 5, but in our set 17. Yes. Which of the following would have the permanent dipole moment? Now silicon tetrafluoride. Yes. So structure is what? Silicon tetrafluoride. Yes. So here structure is tetrahedral. Tetrahedral. So what about here dipole moment? Mu is equal to 0. Yes. Now what about BF3? Planar molecule. Trigonal planar. So mu is equal to 0. Now come to the xenon tetrafluoride and sulfur. Okay, tetrafluoride. Xenon tetrafluoride. Xenon has valency electrons how many? 8. So how many they are bonded with the fluorine? 4. 1, 2, 3, 4. Now after using 4 electrons, okay, sharing with fluorine for bond formation, this xenon has how many lone pairs? It has the 2 lone pairs. So one lone pair present what? Okay, one lone pair is above the plane. What about one lone pair? Below the plane. So by this way, okay, due to the two sides occupies of the 1 lone pair in the case of the xenon tetrafluoride, that made this structure square planar. Due to the square planar, the dipole moment of this xenon tetrafluoride is 0. Yes. Now by this way we got molecule A 0, We got molecule C 0. We got molecule D dipole moment 0. But what about in the case of the sulfur tetrafluoride? What about the valency electrons of the sulfur here? 6. How many sulfur used? 2. Fluorine? Yes, fluorine it used 4. Yes. Remain how many? Remain 2 in the form of the lone pair. Now tell me what about the geometry of the sulfur tetrafluoride pyramidal? So due to the pyramidal here, okay, what about the geometry? Unsymmetrical. So unsymmetrical molecule, dipole moment is not equal to 0. Then it is as dipole moment, that dipole moment is permanent dipole moment. Yes. Now what is the answer? Answer is in the case of this question. Yes, what is the answer? Answer is sulfur tetrafluoride has, yes, it would have a permanent dipole moment. Clear? So its dipole moment is permanent. Now next question. Next questions are all the bond parameters regarding this in this section only. All are dipole moment only. Now H2O is dipolar where BeF2 is not. Yes, already we learned this also. Yes, what is the question? 18th one. 18th one question is why H2O is dipolar? Yes, due to what? Angular shape. Oxygen, hydrogen. So shape is angular. What about here? Beryllium difluoride? Linear. Yes, then what about it is dipolar? Polarity is there. Here polarity not there, 0. Yes. So answer is D. Next question number 19. Example number 19. Yes. So what is this? Which of the following molecules does not possess a permanent dipole moment? Yes, permanent dipole moment. Yes. So we see here carbon disulfide. Okay, no permanent dipole moment due to the structure. Carbon and sulfur. Yes. So what about SO3? H2S, SO2. Yes. They have permanent dipole moment regarding the structure. Yes. As the next question, question number 22. Which of the following bonds will have most polar? So how we can decide the polarity of the bonds? Okay, depends on again electronegativity. Electronegativity difference is large. So electronegativity difference is what? Lot of different are large different. So that bond possesses what? Most polarity. So what is the answer then? So answer is C. Nitrogen chlorine, electronegativity is same. Oxygen fluorine, small different. But nitrogen fluorine, lot of the difference between, yes, what? Electronegativity. Yes. So answer is what here? Nitrogen fluorine. NL contain the same atoms. Yes. Answer is what? Answer is NF. So here, so answer is C. Correct. Next, which compound exhibits maximum dipole moment? Yes, here all are benzene derivatives. So which one has here? Okay, maximum dipole moment. So here what about here? Less different. Okay, here distance is very less. Here no, it is wrong because no comparison. Here what here? Lot of different is there. Yes. So then, so we say here dipole moment is maximum. Here dipole moment is less. Clear? Now next question. Yes. So dipole moment of which ketone is maximum? Yes. So we have here all ketones because every molecule here contain what? Ketone functional group. See the A contain functional group of the ketone. Yes, B also ketone. Yes, all are contain ketone functional groups. Now our work to find out, yes, to find out which ketone has maximum dipole moment. Yes. So here ketone C has maximum dipole moment. Yes. Okay. By this way, so we got here, okay, what? Dipole moment examples. So these all dipole moment examples once again explaining for us. Yes. So how dipole moment is possible in covalent molecule, and this dipole moment very useful to calculate the ionic character in covalent molecules. Yes, so we understood from this topic what, so all covalent compounds, they are not 100% covalent, because due to electronegativity different, they have what, ionic character, so that we can calculate by with the help of dipole moment. Now see, from our Spark Academy side, subscribe to our channel and press bell for notifications. You will get all entrance notifications and recording, recording the matter also you will get. Here the videos playlist available. They are recording the JEE, NEET, Eamcet and IIT Foundation for 8, 9, 10 classes also. And see, so congratulations to all students. It is our result graph. So every year our result is increasing, and it is highest score and selections from our Spark Academy students. So thank you.